Swayam Prabha. Digital India. Educated India.
Good morning. Today we will be talking about C space as a manifold. In the last class we looked at topology. So today we will be looking at specifically the topology or the structure of the C space, which we call the manifold. Okay, so let us very briefly discuss about what we had done in the last few classes, and then see that how we can represent the C space as a manifold. What are the properties and why is it important? So if you remember, in the last few classes we talked about configuration space of a mobile robot, then we talked about configuration space of a serial arm robot, and the configuration shape of the configuration space of a mobile robot is to that side. So the configuration space of a mobile robot, we develop it by making the robot into a point and by increasing the obstacle. This is going to become xy only. Okay, so this is my x, that is my y. So the configuration space is essentially 2D. Okay, but now when we talk about a serial arm robot having 2 degrees of freedom, so what would the configuration space of that look like? So we will very briefly look at how we derived it or how we drew that, and let me draw a 2 degree of freedom serial arm. So 2 degree of freedom arm is drawn like this, and this is my xy, and this is my theta 1, and that is my theta 2. So we have seen that when I want to draw the configuration space of this robot, essentially I am going to vary my theta 1 from 0 to 360 degrees, and I am going to vary theta 2 from 0 to 360 degrees. And if you look at the right side figure, then if I say that this is my theta 1, so if I start from here and say this is my theta 1, and theta 1 is going to vary like this from 0 to 360, then I get a circle. Now at every point on the theta 2, okay, on every point on this theta 1, what happens is theta 2 can vary from 0 to 360 degrees also, so I get one more circle like that. Okay, so for every point here I get one more circle, which is shown by the black one here. So you can look at this black circles, which are basically theta 2. So theta 1 is in this direction and theta 2 is in that direction. Okay, now if I combine theta 1 and theta 2, then what is going to be the shape of the C space? That is the question, and what we looked at in the last class is that the shape is what we call a torus. Okay, so the shape is toroidal in structure, and we represent it like this, which is a torus. Okay, so the configuration space of a mobile robot is more or less similar to our, it is same as our xy space, Cartesian space x and y. Okay, but the shape of my C space of this 2 degree of freedom arm is a torus. Now something interesting here is, as we look further today, is we will talk about the C space as a manifold, or what is the structure of the C space, which we study in terms of topology. Okay, now how do we represent this? Okay, what do I mean by how do I represent this? When we looked at a mobile robot, okay, let me draw that fellow again. So it was a circular mobile robot, okay, and there was an obstacle, for example. So I convert this into my C space. So the mobile robot becomes a point, and the obstacle becomes a C space obstacle. So this is C space obstacle. So let us call the C obstacle, and this has become my point robot. Now I could represent it in xy, which means essentially it is still in 2D, okay, for a mobile robot. Now for a serial arm robot, the dimension of this configuration space, so if I talk about the dimension of C space, this is also 2, because there are 2 variables, 2 degrees of freedom, which is theta 1 and theta 2, okay, which is very clear from here that the dimension of the configuration space for a mobile robot is 2, okay, and that of a serial arm is also 2. Okay, but I could represent the C space of a mobile robot in my xy in 2D, whereas I cannot represent the C space of a serial arm in 2D, because I cannot draw this torus in 2D. So if you look at this torus that I have drawn, it is actually drawn in 3D. Okay, so this the drawing, so draw torus, this is in 3D actually. Okay, so this question of how can you represent C space, okay, is very important here now, that we can represent the C space of a mobile robot in x, y in 2D. The dimension is also 2D and you can draw it in 2D, whereas for the serial arm robot, although the dimension is 2D, degree of freedom is 2D, when you are drawing it, you are actually drawing the torus in 3D. Okay, you will not be able to draw a torus in 2D. It will become, if I try to draw a torus in 2D, it will become something like this. Okay, so this is something that's important to note, and we will see as we go further that how do you represent it. Okay, now let's go further. We also talked about the toroidal space, that if I were to cut it, it's very difficult to visualize this space. Okay, in this toroidal space. Now, if there were obstacles, then the obstacles will be somewhere here. Let's say there is an obstacle here in all kinds of shapes. We have seen in the last class that there is very little correlation between the shape in 3-dimensional world and in the case of the C space world. Okay, so a circle can become all kinds of crazy shapes. So similarly, if there is an obstacle, so we have a 2 degree of freedom arm like this, and we have an obstacle there. This is a circle, but this circle will not remain a circle here on the toroidal space. It will become some other shape. Okay, so to look at that shape and then to do path planning on this toroidal shape is very difficult. So what we do is basically we cut it. So we say that in this toroidal space I will cut it here. So let's say I cut it like this, okay, and open it up. So if I cut it and open it, it is going to be a cylinder. Okay, then I cut the cylinder like this. So I cut it along this axis also, and then convert it into a xy kind of a. So this is my theta 1 and that's my theta 2. Okay, so this next slide actually shows that if you have a surface like this, you can roll it, and then you can so this is rolled about one axis, and then roll it about the other axis, about 2 different axes, and then you get the torus shape. So this is my torus shape. How did we get it? We rolled it about this axis. So this is rolled about this axis, then I roll it about that axis. Okay, so these are 2 axes I'm rolling it against, and then we can get a torus. Okay, so that is how we convert the torus into this xy kind of profile. So this is my xy of the torus now, the cut torus. So this is my theta 1 and this is my theta 2. Now if you are wondering why do we do that, I just explained that path planning on the torus would be very difficult because it's very difficult to visualize. Okay, whereas in this we are more used to looking at xy spaces, and here we can very easily find out which is free space, which is obstacle space, and then do our path planning. So very quickly revising, what we had done is we saw C space of a mobile robot, C space of a 2 degree of freedom serial arm. Today we will see how do we represent it, okay, and then see the structure of the C space, which is a manifold. Now we were trying to correlate. Okay, we said that we are going to cut the toroid and then make it into stretch it out, and it will become xy kind of a plane. So that if we have a serial arm like this, where we have one arm here and we have another arm there, okay, and I'm going to draw the equivalency space here. So this is the equivalency space here. Then each color of the obstacle. So this is my O1, this is my O1, this is my O2, this is O2. So the color represents each of the obstacles, and you can see that there is very little correlation between the shape in the 3-dimensional world for an obstacle, 3-dimension or 2-dimension, to the C space world. Okay, so there is very little correlation there, but we can very easily find out the, for example, this link when theta 1 is equal to 0, this is going to be hitting the obstacle from this range to this range. Okay, so theta 2 is that range where it is going to hit, and that is actually showing. So theta 1 is equal to 0 corresponds to this, and the space where it is hitting is corresponding to here. So you can get this correlation. Okay, so we also looked at in the last class how to draw this and how to write a program which can actually draw this from our Cartesian world. This is Cartesian xy, from our Cartesian space to C space. Okay, that we could write a program which can actually do this. Now let's look at further that we are trying to look at the topology of our C space now. Okay, what is the structure of this space? That is what we are trying to look at today. Now we discussed that topology is a branch of mathematics that considers properties of objects that do not change when subjected to arbitrary constraints. Now what is the need for this topology, or what is so special about here? The motivation behind topology is that some geometrical problems, okay, depend on not on the exact shape of the objects, but rather on the way they are put together. Okay, so when we are looking at this kind of a geometrical problem, why are we calling this a geometrical problem? If you look from here to here, how did we draw from here to here? It is basically geometry we are dealing with. Okay, so this is varying, theta 1 is varying from 0 to 360, theta 2 is varying from 0 to 360, means the link is moving in space. and wherever it is hitting or it is not hitting. Those are only two conditions, binary conditions. Okay. So that is essentially a geometrical problem. So this is a geometrical problem, and that is why we are looking at topology, which is essentially topology is the branch of mathematics that deals with this type of geometrical problems. And what kind of problems? These are objects that do not change when subjected to continuous deformation such as stretching or bending. Okay. Now a topological space like a C space is endowed with a structure called the topology, which allows continuous deformations of subspaces and more generally all kinds of continuity. Okay. So the topological space is endowed with a structure which is called the topology. So today we are trying to look at the structure of a topological space. Okay. So this is to convince you that this is essentially a geometrical problem, okay, and that is the reason we are going to topology now, and we are talking about the topology of configuration space. So topology is the intrinsic characteristic of a space, and two spaces have different topology if cutting and pasting are required. If they are subjected to bending and stretching without cutting, then they are still in the same space. For example, on a rubber sheet, if you draw a square, okay, or if you draw a circle, I draw a circle. If I stretch the sheet in this direction, what will happen is the sheet will get stretched and the circle will become an ellipse. Okay. But it does not change in the sense that points which are inside the ellipse will still remain inside, they cannot come outside, and you can bend it and twist it and do all kinds of things, but points which are inside will still remain inside, okay, they won't come out. So in that sense, this space and this space is the same. So a square and a circle in that sense are the same in terms of topology. Now the path planning algorithm that we are going to do is going to be on the C space, okay, which is a topological space, and you have to go in between spaces. What I mean is, from Euclidean space, Cartesian space, we go to C space, from C space we do the path planning, come back to Cartesian space. So there is this mapping which goes on from the Cartesian space to the C space. Okay. So there is this continuous mappings which are going on. So there is a forward direction, okay, forward mapping, and there is an inverse mapping which is going on from the C space from the Cartesian space to C space, and then back from C space to Cartesian space. Now what are the different spaces? We have Euclidean space XYZ, which is represented by R. So I will be representing this by R. Then we have C space, which is θ1, θ2 for a 2 degree of freedom mobile robot, or is XY in the case of a sorry, is 2 degree of freedom for an arm robot. θ1, θ2 is for an arm robot, and it is XY for a mobile robot. Okay. So for a mobile robot, it is simply XY. Okay. Now the path is in C space, whereas the robot moves in Euclidean space, and hence there has to be some relation between the C space and Euclidean space. Okay. Now if there is no relation, then what will happen is this mapping will break down. Okay. Now what I mean here is that we have an arm manipulator. Let's look at this example. Okay. How does this manipulator move? At every joint there is a motor. Okay. So there is a motor which is actuated from the controller. The motor rotates, theta rotates, and theta rotates, that xy changes. So there has to be some relation between x and y is a function of θ1, θ2 in this case. This is the forward mapping. In the inverse mapping, we will have θ1, θ2 is the inverse of xy. Okay, so that is the inverse mapping. Okay. Now suppose this inverse mapping does not exist at some point, that means you cannot achieve that velocity or you cannot go to that position. Okay. Especially in terms of velocities, we will look at this mapping. So there is a forward mapping. So this is my forward mapping, and this is the inverse mapping. Okay. So this mapping will take you from one space to another space. So this is one space, this is another different space now. Okay. So when we are looking at this forward and inverse mapping, if the mapping does not exist, then the part cannot be executed by the robot. Okay, that is what it means, and hence this mapping is very, very important. Next, how do you represent the C space? Okay. We have seen that if you have a mobile robot which is a point, it can simply be xy. Suppose you have xy and theta, then what? Okay. Then on the serial arm it can be θ1 and θ2. Okay. These are all C spaces. Now how do you represent this? Okay. So now let's look at let's see further. In terms of topology, we have said that topologically speaking, they are spaces or objects which can be subjected to bending and stretching, and they are the same object of the same space. And here basically, for example, a donut and a mug are the same topological space because it can be deformed and you can get different shapes. Okay. So essentially they are the same, so as far as topology is considered. Now, there are many examples like that. Now, this deformation from one space to another space is basically what we look at the mapping between two spaces S and T, which are classified under homeomorphism and diffeomorphism. Okay. So, first of all, this phi S to T essentially indicates a mapping. So, there are two sets, one set is T and the other set is S. Now, these mappings that are going on, one to one, many to one. Okay. So, there are different mappings possible. So, when we look at this mapping which is going from S to T, then we represent it this way: phi S to T places elements of S into corresponding elements of T. Now, if all elements of T are covered by the mapping, then it is called a surjective mapping. That means all elements of here are covered in this mapping, then it is called a surjective mapping. Now, if each element of T has correspondence with at most one element of S, then this is called an injective mapping. So, if there is a mapping in which each element of T is corresponding to at most one element of S, then it is called an injective mapping. Now, if phi is a surjective and injective, then this is called a bijective mapping, okay, in which case an inverse exists. Okay. So, we were talking about forward and inverse. Okay. So, this is the reason we were talking about an inverse also. So, if a mapping is surjective and injective, then it is called bijective, and if phi is smooth, its derivatives of all orders exist, or we say it is C infinity continuity in terms of C infinity. Okay. Now, if a mapping is bijective, okay, and both phi and phi inverse are continuous, then it is called a homeomorphism. Okay. Why this question of continuity or continuous? Because of path. Okay. We said that a path has to be continuous. Okay. You cannot have a discontinuous path. Why? Because the robot will not be able to go on that path, okay, if it is not continuous. Why will it not be able to go? Because when we are talking controlling the robot, we have to talk in terms of theta, we have to talk in terms of theta dot, and we have to talk in terms of theta double dot, which is a trajectory. Okay. So, if it is not continuous, you will not be able to get the first derivative, second derivative, and hence you will not be able to follow, or you will not be able to form the trajectory of the actuator. Okay. So, now we said that if phi S to T is a bijection and both phi and phi inverse are continuous, then this is called a homeomorphism. Okay. And if such a phi exists, then S and T are homeomorphic. Okay. So, this is the term which we call homeomorphism, which basically means that the mapping is bijection and both phi and phi inverse exist. Now, if a map phi u to v is called a diffeomorphism if phi is bijective and phi inverse is smooth. Okay. And what is the meaning of smooth? Smooth essentially means that if derivatives of all orders exist, okay, then u and v is a diffeomorphism. Okay. So, we have two terms, homeomorphism, which is phi is a bijection, that is surjection and injection, and phi and phi inverse are continuous. Now, what is a diffeomorphism? Diffeomorphism is essentially if phi is a bijection, is bijective, and phi inverse is smooth, then u and v are diffeomorphic. Okay. So, these are the two types of mappings which go on between two sets S and T. Now, why is mapping important? This I have said quite a few times, that we are basically going from one space to another space. So, path is in C space, whereas the robot moves in Euclidean space. So, if there is no connection, then obviously you can find a path, but the robot will not be able to go on it. Okay. The second reason being is that paths in the same space can be carried over. Okay. In the same space means same topological space can be carried over. So, if I make a path for a mobile robot in one space and I change the robot a little bit, okay, then the same path can be carried over to another mobile robot which has the same structure in the same space. Okay. So, paths in the same space can be carried over from one space, can be carried over from one robot to another robot. Okay. So, basically what I am trying to say is that the paths in the same space can be carried over for different robots if the C spaces are the same. Okay. Now, so this is the first point. The second is paths, and I would also use the term algorithm. So, the same algorithm can be used for different robots if the C space is the same. Now, let us look a little bit more about the mapping between Euclidean space and C space. Now, first of all, why was it possible that we could go from Euclidean space to C space and come back to Euclidean space again? Okay. Now, in the C space that we have seen so far, they could be specified by n parameters, where n is the dimension of the C space. Okay. So, all the C spaces that we have seen, one for the mobile robot and one for the serial arm, they can be specified by n parameters, where n is the dimension of the space. So, in the case of the mobile robot, if it is a point, its x, y dimension is 2 and degree of freedom is also 2, whereas for the serial arm, the degree of freedom is 2, which is theta 1, theta 2, and the dimension of the C space is also 2. Okay. Now, for planar mobile robots, where we have x, y and theta, so we have x, y, so we have x, we have y and we have theta, then n is equal to 3, which is the dimension of the C space, while for a 2 degree of freedom arm, it is n is equal to 2. Okay. Now, the reason we were able to do this is that C spaces are locally like n dimensional Euclidean spaces. Okay. So, we were able to represent the C space by n parameters. Okay. Why? Because the reason is that the C spaces are locally like n dimensional Euclidean spaces. So, this term is very, very important here, that C spaces are locally like Euclidean spaces. And what does this further mean? That the C space is actually a topological space which we call the manifold. So, a manifold is a topological space that locally resembles Euclidean space near each point. So, every point on the C space you can find a region in the Euclidean space where it can be mapped onto, okay, but it is locally. Okay. The structure of the C space is called a manifold that resembles Euclidean space near each point. Okay. So, C space is a manifold and it locally resembles the Euclidean space near each point. Okay. That is the reason why you are able to go from one space to another space, and the dimensions are the same also. Now, for each point Q, there is a one-to-one map between a neighborhood of Q and a Euclidean space r raised to n, where n is the dimension of the C space. Okay. So, first of all, C space as a manifold, we are talking about C space as a manifold. So, what is a manifold? A manifold is a topological space that locally resembles Euclidean space near each point. Now, in terms of definitions, so this is the definition of manifold. A set K is a k dimensional manifold if it is locally homeomorphic to R, meaning that each point in S possesses a neighborhood that is homeomorphic to an open set in R, okay, which essentially means that every point locally resembles the Euclidean space. So, every point in the C space can be mapped locally onto the small neighborhood in Euclidean space. So, this is the meaning of C space. C space is a manifold, and a manifold is a topological space that locally resembles Euclidean space near each point. Okay. Now, this is very, very important for us, because what it also basically means that I can represent a circle. So, a circle is a manifold and it is topologically similar to a line of dimension 1, which basically means that if I take a very small point here, I can stretch it to a local region here, and then it becomes a straight line. Okay. So, this is the meaning of locally. I can take a point on the C space and it resembles a Euclidean space, okay, locally. Okay. And we should remember that C space is a manifold. Okay. So, a manifold is a topological space that locally resembles Euclidean space near each point. So, this is basically telling us that we can map from this kind of a circle to that of a straight line, but locally for every point. Now, why is this important? Now, again, you can go back a little bit and think that there are applications where we need to do this. For example, this is an application where we are trying to map the world. So, our world, the earth. So, the earth, okay, is rotating about an axis, and we want to make, this is a sphere. So, earth is a sphere. Okay, and we want to make a chart which is basically, so a sphere is spherical, okay, and a chart is xy. A map would be like this. So, basically this is xy, this is getting mapped, or this is getting mapped onto this map. Okay. So, this earth, we are representing the earth in the form of maps. Now, if you look at the structure, this is spherical, so it's a sphere maybe, and so you can say that it is circular, and for a local region there, I can represent this as a map there, okay, which is actually xy. Okay. So, this is the meaning of being able to locally map, okay, from a circle to a straight line, which is shown here. Okay. Now, so we need to have this definition of two terms, which is called a chart and an atlas. So, pair U phi such that U is an open set in a k dimensional space, and phi is a diffeomorphism from U to an open set in R is called a chart. Okay. So, a pair U and phi such that U is an open set in a k dimensional space and phi is a diffeomorphism from U to an open set in R is called a chart. Okay. And a chart is analogous to its use in cartography or making charts. So, cartography is making charts, not making charts, but making maps. Okay. So, in map making we also call this a chart, which is a map, which is essentially 2D. Okay. 2D representation of a spherical surface, which is the earth. Now, a set of charts that are C infinity continuous basically, and those domains cover the entire configuration space form an atlas. Okay. So, a set of charts that are continuous. Okay. So, first of all, a set of charts that are C infinity related, which means continuous, and whose domains cover the entire configuration space form an atlas. Okay. So, at one point we are saying that this we are going to extend it and make it into a map. So, this is a chart. Now, when everything is covered here all the points are covered and they are continuous, then we say that this forms an atlas. Okay. So, it is the same term that is used in cartography or making charts or making maps. So, chart and atlas. Okay. So, what is a chart? So, chart is a pair such that U is an open set in k dimensional space and phi is a diffeomorphism from U to an open set R is called a chart. And a set of charts that are C infinity continuous and are related and whose domains cover the entire configuration space form an atlas. So, we have two terms here, and which is a chart and that is an atlas. Okay. So, these are two terms that are also used here when we go from C space to Euclidean space. Now, an atlas and C space together constitute a differential manifold. So, when we call a differential manifold, then we are calling this an atlas and a C space together constitute what we call a differential manifold. So, we have looked at these three terms which we need to understand very carefully, that C space is a manifold. Okay. That means it has a particular structure. Okay. And it is a topological space. And what is the structure? It locally resembles Euclidean space. Okay. That is the structure of C space. Now, if you want to represent it, then we can represent it as maps, and the continuous collection of maps is what we call the atlas. Okay. And an atlas and C space together constitute what we call a differential manifold. So, this basically gives us a definition of what is a manifold, okay, and that C space is actually a manifold. Now, a couple of more terms before we proceed. Another important term is what is called connectedness. Okay. So, a manifold is path connected or connected if there exists a path between any 2 points in the manifold. Okay. So, we have seen what is a manifold. Okay. Now, we say that a manifold is path connected or simply connected if there exists a path between any 2 points in the manifold. Okay. Now, the presence of an obstacle can disconnect the manifold. Okay. So, if there is an obstacle in the C space, then what can happen is it can disconnect the manifold. So, we are seeing that this example I showed is that we have a 2 degree of freedom arm. This is a 2 degree of freedom arm, and there are obstacles. Now, what these obstacles are doing is they are breaking the connectedness of this C space. So, this is my C space. Okay. If there is no obstacle, let us look at it this way. So, if it is connected, fully connected, if it is fully connected, I have a C space like this, okay, and there is no obstacle. So, you can go from anywhere to anywhere. Okay. So, there is no obstacle here. So, in a C space which has no obstacle, basically we can go from one point to another point which is connected. So, connected means I can go from anywhere. Now, the moment I put an obstacle, okay, so I put an obstacle now, there is an obstacle like this. This is my obstacle now, just for example. Now, this is still connected because this part is connected to this part, there is a connection there. Okay, so, they are connected. Okay. But the moment it becomes like this, where I am fully cutting it through, okay, with an obstacle like this, and I have some other part like this, one more obstacle here. Now, this part and this part are not connected anymore. Okay. So, this is the meaning of what we mean by connectedness. So, a manifold which is a C space, is path connected or connected if there exists a path between any 2 points on the manifold. Okay. Now, if there does not exist a path, then it is not connected. Now, it is very important in path planning, because you cannot have a path between 2 points which are in different which are in non-connected spaces. Okay. For example, look at the example here. This part and this part is not connected, so you cannot have a path like that. Okay. This is the meaning of connectedness, and this is very, very important for from our path planning point of view, because to have a path the space must be connected. And what does the obstacle do? It breaks the connectedness of the path. Okay. It may not break it fully, like in this case you have an obstacle, but it is not breaking it fully, it is still connected, but in this case it is not connected. So here it is not connected, here it is still connected, here it is still connected. Okay. This is the meaning of the word connected. These are examples that we had looked at earlier also. So we have a C space, equivalent C space, 2 degree of freedom. So we have the 0 0 here, and we have one link here, another link there. So this is the first link, the second link. Okay. There is start point here, end point there. Now can it go from here to here? Okay. If you simply look at this figure, it is difficult to say. So we draw the C space. Now in the C space we find that the corresponding obstacles are marked in color, and one of the start points are here and the goal point is there. Now is there a path like that? So this is not connected, so there is no path in there. Okay. So if you want to find a path, the first condition must be that the spaces have to be connected. Okay. So if you need to have a path is in connected space. Now if you look a little further as to this case, now this path is from here to here. Now this is connected because it is in the same space, so this is connected. So which basically means the manipulator can go from there to there, it is in connected space. Okay. The space is connected. Here also it is in connected space, but it is having a wraparound, and this is something that I explained in the last class, that this is a torus structure. So basically I can fold it. So when I fold it, this part joins with this part. Okay. So if you can imagine, I am going to fold it, and then this part joins with this side. That is how it becomes a torus. Okay. So it means that there is a wraparound feature, or they are connected. This side is connected to this side, and this side is connected to this side. Okay. So if there is a path like this, this and this are actually connected, because this side is connected to that side. Okay. When you fold it and join it. Okay. But this side is not connected to this side. Okay. That is not possible. Okay. So in this particular case also a path exists, because it is in the same connected space. So let us move on now and talk about embeddings of manifold in r raised to n, which is Euclidean space. Okay. Now a k dimensional manifold can be represented by using as few as k parameters. Okay. But doing so may require multiple charts. Now a k dimensional manifold, for example a mobile robot has 2 dimensions x and y, they can be represented using k parameters. Okay. What is the 2 parameters? X and y. Okay. But this has some limitations. Let us have a look at that. So for example S1 is a 1 dimensional manifold, but we need to represent this x squared plus y squared is equal to 1 in R2. Okay. So this 1 dimensional manifold, a circle is a 1 dimensional manifold which is given here. Now to represent a circle you cannot do it in 1D. Okay. 1D means 1 dimension. Okay. This is the meaning of 1D. So you cannot represent a circle in 1 dimension, which means if I want to represent a circle, I have to draw a 2 dimension x and y, and then I can put a circle. So this is x and that is y. Okay. So this said that although this was a 1 dimensional manifold, you have to represent it in 2 dimensions, which is R2. Okay. X and y. Okay. Now similarly we cannot embed a torus which is R2. Okay. A torus is R2, we saw that it is theta 1 and theta 2, the 2 variables, 2 degrees of freedom, but this cannot be embedded in 2 dimensions. That means this is 2 dimensions. I cannot embed a torus, I cannot embed a torus in 2D, I have to embed it in 3D. So the torus that we are drawing is something like an isometric view, and it is actually x, y and z, x, y and z. So this is 3D actually. Okay. So a torus, the way I showed it, is actually represented in 3D, okay, like an isometric view. And so this is a limitation, okay, of trying to embed manifolds in Euclidean space. R raised to n is Euclidean space. Okay. So now what do we do about it? So what we can do about it is we can use multiple charts or use a single global representation by embedding the configuration space in a higher dimensional space. Okay. So, to get rid of this problem, what we do is we are going to use multiple charts. This could be one possibility. Okay. The other possibility is, or use a single global representation by embedding the configuration space in a higher dimensional space. Okay. So, what we can do is we are going to follow this one, try and embed it in a higher dimensional space and see how to go about it. Now, let us talk about x, y and theta. Okay. Theta is the rotation of a body. So, we saw that rotation of a body cannot be represented by one element only. Okay. So, we are talking about the rotation. So, we talked about the rotation of a body. So, we have a mobile robot. Okay. We have its 2 axis. There is a caster wheel in there. Okay. So, this is I can take it with reference to some axis. So, this x axis, that is y axis. Okay. And this is my theta, that is my point x y. So, if I look at the C space of this one, okay, then it has configuration 3, it has 3 dimensions, which is x, y and theta. Now, this one is rotation. So, the question comes, how am I going to represent this? How am I going to represent rotations? Okay. So, that is what we are trying to say, that we have a 3 dimensional space, but I cannot represent x, y and theta in 3 dimensional space. So, what I do is I go to a higher dimensional space, and what we are doing here is we are representing rotations by means of a 3 by 3 matrix. Okay. This is what we just explained in the previous slide, that we are trying to go from we are trying to embed the configuration space in a higher dimensional space. Now, we know that the rotation matrix is a 3 by 3 matrix, and let us talk about the rotation matrix here. So, the rotation matrix, I had in the first few lectures I had explained how we derive the rotation matrix. So, it is a 3 by 3 matrix which has 9 elements. So, cos theta minus sin theta cos theta 0 0 1 0 0. Okay. So, this rotation is being represented like this now. Okay. Now, we can have multiple rotations, and this can have multiple properties. For example, this rotation matrix is a 3 by 3 matrix having 9 elements, but each of this, if I consider this to be x, y and z as unit vectors. So, x, y and z are unit vectors. These are unit vectors which are basically the axis. Okay. So, because they are unit vectors, mod of x is equal to mod of y is equal to mod of z, which is equal to 1, and x into y is equal to x into z is equal to y into z is equal to 1, no, sorry, is equal to 0. So, this basically means that there are 6 constraints. Okay. Now, if there are 6 constraints and you have 9 elements, then you have 9 minus 6, we have 3 parameters which are free. Okay. Now, these 3 parameters which are free are required to define the rotation of a body in 3 dimensional space. Okay. This is the meaning of what we are trying to say here, is that we are trying to represent rotations. Okay. Now, to represent rotations, we need 3 parameters, and these 3 parameters are the 3 angles alpha, beta and gamma, which are the 3 angles it can make with the 3 axis. Okay. And why 3? Because although this fellow is 9, we need there are 6 constraints. So, it is 9 minus 6. So, there are only 3 parameters left. Okay. So, these 3 parameters are the alpha, beta, gamma, which can be which are the representations, which are the angles it makes with the x, y and z axis. Now, properties and constraints we have seen. So, properties, we have seen that the rotation matrix has 9 minus 3 parameters, 9 minus 6, sorry, 9 minus 6 is 3 parameters. Okay. Now, we can have combined rotation matrices. Okay. Now, the question is how to represent any arbitrary rotation of a body. Okay. So, this is something that we need to look at. So, there are different ways by which we can represent any arbitrary rotation. For example, we can have Euler angles. Okay, so we can specify the orientation of a local frame with respect to a fixed frame by 3 angles, which are called the z, y, and z rotations about the rotated frame. Okay, please note that this is my x axis, this is my y axis, and this is my z axis. Okay, so the first axis that we do, the first rotation. So what I am trying to say here is that I am trying to answer this question, that how to represent any arbitrary rotation of a body. Okay, so I can have 3 rotations, okay, and they can be in any order. Okay, so here if I look at one way of trying to represent these angles, which are called Euler angles, then using this Euler angle we can specify the orientation of a local frame. That means local frame is fixed to the body. So let me again draw it here and try and explain it. So this is my x axis, that's y axis, and that's z axis. So I have a rigid body here. So on the rigid body I put a frame. This is my x, that's my y, and that's my z. Okay, so this is my frame. Okay, so I want to find the relationship between the frame x dashed, y dashed, z dashed with reference to x, y, z. Okay, so what are the different ways by which I can do this? By using the Euler angles, which says we can specify the orientation of a local frame with respect to a fixed frame by these 3 angles, and these 3 angles are the 3 rotations. What are the 3 rotations? About z axis, y axis, and then z axis again. So this is my x, y, and z axis. So if you look, the first rotation is about the z axis, which is this one. The second one is about the y axis, which is this one, and then the third rotation is about the rotated axis. So this is my y axis. So sorry, not this one. It is about the rotated system. So this is my first, second is this one, and the third is that one. Okay, so these are rotations about rotated axis. So here we have to remember that rotations about rotated axis. Okay. Now if you have rotations about the rotated axis, then the order of the matrix multiplication remains the same. So I am trying to find the combined matrix of R, let us call it alpha, beta, and gamma, which are rotated in the order of alpha, beta, gamma. Okay, so this is my z, y, z. Okay, in that order, then the multiplication of the matrices are going to be R alpha z, R y beta, and R z gamma. Okay, so the order of the matrix multiplication remains the same. We do not change the order. That means whichever was first, second, and third, it will come in that order only. We are not going to change the order. Now there are other representations we can call the roll pitch yaw, in which case the rotations are about fixed axis. Okay. Now what are the fixed axes? So I have x, this is my x, y, and z. So this is my x axis, that's my y axis, that's my z axis. So the first rotation, roll pitch yaw rotations are about the fixed axis. So first I am going to take, let us say, alpha. Okay, then I am going to take beta, and then I am going to take gamma. Okay, so these are 3 rotations, first, second, and third. Okay. Now if you are going to do a rotation about the fixed axis, okay, then what happens is the order of multiplication reverses. Okay, you reverse the multiplication order. Okay, so this is something important to note. Okay, that depending on how you are representing your rotations, if you are rotating about the fixed axis, if you are rotating about a rotated axis, the order of multiplication does not change. Okay, it remains in the same order. Whereas if you are going to multiply, if you are going to rotate about a fixed axis, okay, what we call the roll pitch yaw kind of rotation, then the rotation matrices are going to reverse. Okay, so the first one was so first is gamma, number 2 is beta, and the third is alpha, beta, and gamma. So that was the order in which I went. Okay, so I am going to reverse it. I am going to make it so this is first, second, and third. So I am going to reverse the order and going to pre-multiply. We are going to pre-multiply. We are going to pre-multiply matrices. Okay, so if you are going to rotate about the fixed frame, then we are going to pre-multiply matrices. And why is this important? Because we know that these are matrices. So A cross B, is not equal to B cross A. Okay. So, these are not equal, and because of which you have to. So, in case of representing these rotations, multiple rotations, we have to be very careful how we are doing that. Okay. And this is very, very important in the case of serial arm manipulators. So, we have serial arm manipulators which can have many degrees of freedom, okay, all kinds of shapes and in 3D, and finally it comes here. So, this can have all kinds of shapes, it can have an axis this side, it can have an axis this side, this can be all kinds of axes. Okay. So, how you are rotating is going to determine how you are going to multiply your rotation matrices at the end of the day. Okay. So, here what we saw is that when we are going to use the Euler angle rotations, which are rotations about the rotated frame, then we do not pre-multiply, we keep the same order. Okay. So, if it is 1 2 3, then it is going to be 1 2 3, but if it is going to be order of multiplication is reversed in the case of rotations about the fixed axis. Okay. In that case you pre-multiply. So, in this particular case you are going to pre-multiply. So, if it is alpha and then beta, so alpha is 1, then number 2 is beta, the rotation matrix is going to become beta and then it is going to become alpha. Okay. So, this is the meaning of pre-multiply. Okay. So, this is the meaning of what we mean by pre-multiply matrices, we are going to reverse the orders. Okay. So, this is very important from our point of view that we are talking about trying to represent the C space which has xy, and it also has a theta, it has a rotation. Now, how do you represent that rotation? That is in the form of a matrix now, and if you are using a matrix, then we have to worry about if there are multiple matrices which are coming, then whether about which frame are you rotating, that becomes very, very important. Okay. Now, if we move further, then we are trying to represent the position and orientation of a rigid body. Okay. So, in the previous case that I drew, this is just showing the angle between this and this. Okay. This is not showing the linear displacement here. Okay. Now, suppose I want to have two frames x, y and z, and I have a local frame here which is x dashed, y dashed and z dashed, and I have a body here which is BP, okay, and this is my frame A. Then what is the relation between this frame and this frame? That means the coordinate of this fellow UVW with respect to AP, which is XYZ. Okay. So, this has a position and it has an orientation also of a rigid body. Okay. So, how do I represent this now? Okay. So, what we can do here is we represent this by we cannot represent this by 3 by 3 matrix, because in a 3D Euclidean space there are only 3 parameters, right, and these 3 parameters are taken off by the rotation matrix. Okay. So, the 3 parameters of the Euclidean space, 3D Euclidean space, are already gone. Okay. So, we have no more parameters. So, we have to move into a higher dimensional space, which is basically called the 4D homogeneous space. So, this is called the 4D homogeneous space, which can take care of the position plus orientation. So, position plus orientation is taken off is in 4D space, which is 4 by 4, and we had derived this matrix a couple of classes back, I think the first lecture or the second lecture. Please refer to that how do we derive this matrix, and basically this matrix T matrix comes in the form of, it has 4 parameters. This is cos. So, the first one is rotation, and the rotation part, let us call it cos theta minus sin theta cos theta 0 0 1 0 0, this is 0 0 0, this is del x del y and del z, this is 1. Okay. Now, this is the rotation part. So, this is my rotation matrix, this is the translation part, and this is called the scale, it is always 1, and this is called the perspective. Okay. So, rotation, translation, scaling and perspective. So, what we see here is that we are trying to represent this position and orientation of a rigid body, and it cannot be done in a 3 by 3 matrix, it is a 4 by 4 matrix now. Okay. Now, something to note about this is that when we are going from here to here, so I have frames which are assigned Z0, Z1, Z3 and Z4. So, this is my x axis, these are the various x axis, this is x4, this is x3. Okay. Now, each of this, if I want to go find the relation between that one and 0 frame, then it is basically saying T0 to 4, and I find the matrices between each of the frames and multiply them out. This gives me the relation between the 4th frame and the 0 frame. Here we note that the order remains the same. Okay. So, we are not reversing the order by which we are going. Okay. In the case of the rotation matrices, depending on which axis you are rotating with, you have to be careful of that order. Here the order remains the same. So, from 4 to 1 it is simply going this way. Okay. So, this gives us the relationship between matrices which are rotation matrix and translation and rotations together, and this we are trying to answer because we looked at this point that how do you embed the manifold in Euclidean space. Okay. So, how are we going to embed the manifold in Euclidean space, and we saw that what we do is we use a single global representation by embedding the configuration space in a higher dimensional space. So, my higher dimensional space is 3 by 3 the rotation matrix or the 4D homogeneous matrix here. Okay. That is how we represent rotations and translations in higher dimensions. So, this gives us the basic understanding of how do we represent rotations and translations. Now, let us look at what we talked about, the mapping, that now these are some examples. These are some examples of dimension of space. For example, a mobile robot translating in a plane is 2D, it is just xy. Okay. So, it is r raised to 2. Okay. The dimension is 2. Now, mobile robot translating and rotating is x, y and theta. Okay. So, this is 2 dimension, this is 3 dimension. So, it has x, y and theta, and that theta fellow is represented as a matrix now. Okay. Now, a rigid body translating in 3 dimensional space is R3. So, it is 3, it is x, y and z, it is only translating. A spacecraft free floating, which we call a free floating body. So, a free floating body is having x, y, z, and it is having 3 angles. So, it is 6. Okay. So, x, y, z and alpha, beta, gamma. So, x, y, z and alpha, beta and gamma, 3 plus 3 is 6. Okay. N jointed revolute manipulator is T raised to n. So, n is the degrees of freedom of that. So, it is n here. Okay. A planar mobile robot with an attached n degree of freedom arm. So, the planar mobile robot is 2, this fellow is 3. So, T raised to n. So, it is this many degrees of freedom. Okay. So, this basically gives us examples of how many degrees of freedom are there. Now, before we end off, let us look at mapping between velocity and joint angle, which is called the Jacobian. Okay. So, we looked at the Jacobian in the second lecture, I think, or the first lecture, and we said that if this is my angle theta 1 theta 2 and this is x y, then we can write this equation x is equal to L1 cos 1 plus L2 cos 1 2 and y is equal to L1 sin 1 plus L2 sin 1 2. Okay. So, x y is related to the joint angles this way, and and I can write this by taking the derivative as x dot is equal to minus L1 sin 1 minus L2 sin 1 2, and this is minus L2 sin 1 2. This is L1 cos 1 plus L2 cos 1 2, and this is L2 cos 1 2. I can write it this way in matrix form. So, this theta 1 dot and theta 2 dot. Okay. So, now what we can say is that this gives us x dot is equal to j into theta dot, where j is called the Jacobian. Okay. So, x dot is equal to j into theta dot. Now, this is my joint velocity. So, if I want theta dot, I need j inverse into x dot, which is equal to adjoint of j by determinant of j into x dot. Okay. Now, if determinant of j were to become equal to 0, then this mapping will break down. Okay. And such points are called singular points. Now, the determinant of j is equal to L1 L2. You can find out, you can multiply this this into that minus this into this, and what we will get is L1 L2 sin 2. So, if sin 2 were to become equal to 0 or 180 degrees, this mapping is going to break down. Okay. So, this means that there is no relationship between this and that if this fellow becomes there is no relationship between the inverse mapping from here to here if this fellow breaks down and goes to infinity. Okay. So, this is again showing us that it is very important to understand this mapping which is going from one space to another space. Let us have a look at a very simple example of a mobile robot again. Okay, this is my F, let us call this FR, the global frame, and we have a mobile robot which is placed here. Okay. So, mobile robot has a frame. Okay, so this is my mobile robot frame Fx and Fy. This is my point. Let us call this and this is another point which is R1 R2. So, R1 R2 is in frame, let us call this Fb. So, R1 R2 is in frame B. This is the global frame which is in frame R. Now, what I am interested in is this is my, this is Q1 Q2. So, this point is Q1 Q2 and there is a Q3 which is my angle theta. Okay. This is the point R1 R2. Okay. Now, let us call this point R1 R2 in frame B. Now, X1 X2 in frame R. Okay. So, what we are saying is this is a global frame, this is my X global, that is my Y global, this is a local frame which is fixed on the robot, and on the robot frame this point has coordinates R1 R2. Okay. Now, on the global frame this is X1 X2 on the global frame. So, if you write down the equation X1 is equal, so this is actually my angle, this one is Q3. Okay. So, X1 is equal to, and X1 and X2 what are they equal to if I write it in matrix form, is equal to Q1 Q2 which is the point here. Okay. Q1 Q2 are that point, plus there is a rotation matrix. So, it is cos 3, let us call it cos Q3 minus sin Q3, okay, and there is sin Q3 cos Q3 and this is R1 R2. Okay. This is giving me the relationship of this point here. So, let me mark the point with the red color. So, this is the point here in frame in the global frame is given by this relationship. Okay. Now, if I take the derivative of this, then the derivative of this will become if I take the derivative of this full fellow. Okay. So, if I take the derivative and multiply, then what will happen, x dot x1 dot and x2 dot will become equal to a matrix which is 1 0, okay, 1 0, then this becomes minus R1's Q3 minus R2 sin Q3 and this becomes equal to 0 1 R1 cos Q3 minus R2 sin Q3. Okay. Okay, this is what it becomes. Okay. So, if I take the derivative of this, then what we are going to get is this term. Okay. So, how did I get that? So, I am going to write so x dot is equal to j into q dot and j of q is equal to d phi by dq1, so which is given by this. Okay. So, now if I write it this way, what we do find is that this matrix here is a 2 by 3 matrix. Okay. So, if I take if I write this as d phi by dq, okay, then we find that this fellow is 2 by 3 matrix. So, what this basically means that if you want to find the inverse mapping of this, the inverse mapping of this is going to become many is to 1. Okay. You will not be getting a unique solution 1 is to 1 here. Okay. So, this is an example which shows that if we have because this fellow has 3, okay, and this is only 2 x and y. Okay. If you are trying to go in the forward direction, then this is my equation, and if you are trying to go in the inverse direction, then what is going to happen is you will end up getting multiple solutions. Okay. This is actually showing us the concept of homeomorphism and diffeomorphism. And now from the next lecture we will be going on to the various path planning methods. How do we plan various path planning methods, what are the methods and how to implement them. So, we find the C space. Now, in the C space we have to do the path planning, we have to find the path. So, let us stop here today. Thank you.